Alright, I'm about to start. I have it streaming in the background over here, so I'll be listening. Make sure the audio is coming through. Okay, so let's go ahead and get started. For those of you who couldn't make it the other day, for whatever reason, everything is okay. We're going to kind of be buzzing back through that material to make sure no one's left behind. And it's kind of related to, first of all, this, I don't know that, I can't see the title of the book, but this is the book by Hibbler. It's in the syllabus. So if you can get a new or even a moderately modern version up to the 10th edition, everything is pretty much the same here. So when we look at things as scalar and vectors, we've got two things. So for example, if you were sitting here and you were looking at a map of, say, Rothwell Hall, and say, okay, let's go over here and open a new page and just set that here. Let's say you were sitting here looking at Rothwell Hall, and then over here is the place to eat. And somebody said, "Oh, well, if you want to go get something to eat, just walk 500 feet." Well, half the people that flow out of Rothwell walk over here. If you remember, Highway 7 comes here. You might get hit by a car, but that would be bad. There's a street that comes down right by it. You might be wandering around in the parking lot. Some people might end up in this building, and some people might end up here. But everyone wanted to go right here. This was your target. So not only is the distance important, 500 feet, but the direction. It's that simple. You can see that on a map. If you look at a map, you'll see north, east, west, and south. First thing you realize is you got to figure out your orientation, which direction you're going to go, then find out how far you're going to go. So you've got two parts to a vector. You've got the scalar part, basically the magnitude or the distance you're going to walk, and then the direction you're walking in. Often what happens to us later on is we're basically dealing with directions that are related to, and I'll go ahead and put this on here, north, south, east, and west. But then when you're dealing with scientific things, they start looking at things like this. They say, well, west is equal to a negative east, and south is equal to a negative north. And then they drop these two coordinates, and they figure that this is all you need is an XY. And so, and then if you're going to be in three-dimensional space where you're not just moving along the ground, you're going to need a Z coordinates too. So if you cross X and Y, you'll get a Z. That means this is a right-handed coordinate system. The directions, the best thing for people to do is come up with base vectors, I, J, and K. This is nothing normal. You were taught this in physics and in some math courses. However, his approach during this section is a little bit different, and I'll show you why. So he goes in and talks about vector operations. Okay, you can walk twice as far in the same direction, you'll get twice as far down the trail. Somebody else can walk the other way, like east is a negative west. That's fine. Also, you can do negative and you can do a scalar component of both. That's all great. You get down here, then you can add them together, and then they've got this thing called the parallelogram law. Why is it important in statics and we don't just go straight to IJ? Well, I'll show you why. Well, let's go through this. Okay, you got two ways to add. You can add A, then B, or then you can add B and then A. You get the same distance and direction either time. The resultant's the same here as it is here. Doesn't matter whether you added B to A or you added A to B. Doesn't matter. If you add them directly in the same direction, that is actually the largest value you can get. There's a mathematical law about that, where if your length of A is this and your length of B is that, your length of the resultant has to be, wait a minute, the length of the resultant has to be less than equal to the length of A plus the length of B. What I mean by that, this distance here, from here to here, is shorter than the distance from here to here plus the distance from here to here. That's a common rule in mathematics, attributed, I think, to Schmitz. So you get down here, you got vector subtraction. Well, all it is flipping the direction of the vector and adding the vector. Vector addition of forces. Here's why the vector addition is done this way first here. I have a cable holding a weight up here. If, in fact, this were pulling this way, the cable would align itself such that it would go in the direction opposite to the tension in this chain. I'll call it C. So the force resultant is going to be equal and opposite to that. This is part of statics. So in essence, the vector addition of this and this together visually is such that you take this vector, you can, okay, without too much hassle, hopefully, believe you can do that, and you can take this vector and move it down here, and you would get the same result. So you can take this vector here and move over here. So that's the parallelogram rule, so to speak. Let's take a case in point. Okay, so again, here's the same picture, maybe zoomed out. You have a forklift holding a chain, and down in here is the container with some material in it. Say it's 100 pounds. If you draw a straight line, which actually that's supposed to be a straight line, let me see if I can draw a little bit better of a straight line. Then this is 100 pounds in the opposite direction. If, say, case in point, if, say, you had a vector and you said, here's a vector A, and here's a vector B. Now, you know going together, the weight has to go straight down. So these have to add up such that they go straight down. So, in other words, this is the tension in the chain, cable, whatever it is. This is the weight. It has to go straight down. So I have to be able to take this vector, move it over here, and it has to be such that, okay, let me see if I can write over here, such that its major length can only be this. So this means B is actually, hopefully I can copy this back over, that is B. Now let me try to see if I can do a little bit better job here. Let's see, there was a ruler out here somewhere, ruler. So if I want to be precise and I just want to make things look a little bit better, then I can just draw, say it comes down at 28 degrees. Now I know that's what it comes down at. So let's just draw a straight line. Then what we're going to do is come down here and draw this straight line here. But this time, I'm going to draw this straight line such that it only touches that. Okay, so if it came down at 28, that's fine. I can take this, copy it, back up to right here, put an arrowhead at the end of it, and that's the actual B vector, such that A plus B goes straight down. Okay, that's your reasoning to do this way. Now, go back to the book. How do you do it? Well, what he does, he gets down through here. He ends up with this kind of stuff, where if you got 3 chains, for example, you just do 2 of them together. Then you get the resultant, and then you take that resultant and add it to the resultant this way to get the complete resultant. So you're multi-staging it. What you're doing is F1 plus F2 equals to F12. I'll call it F12 there. Then what you do is F12 plus F3 is the F resultant. So essentially you're saying, I'll do this in multiple stages here. I'll deal with these 2 chains first and get the resultant that way. Then I'll erase these from my mind and consider it as though there's 2 chains, one going here, one going here. Then I'll have the value here, which is F12, and then I'll add it to F3 to get the resultant. Okay, now, how do you do this mathematically? Well, here's how you do it. There's a thing called law of sines and law of cosines. We covered this in class, and this relates to this triangle. Although there is one law of cosine, in this particular case, there are 3 of them. For example, A is equal to B squared plus C squared, square root, minus 2BC times the cosine between B and C, which is A. So there's this one. And then you can list it this way. B is equal to square root of A, oops, that's an A, plus C squared plus 2AC, cosine of the angle between A and C, between A and C is the B. So how does this play out, okay, in an actual problem? Let's come up, now I have this so I can kind of get an approximate value here. I've got marks up and down these scales here on the ruler. So I'm going to use that. Let's say one is tilted down at 54 degrees. Here is your 0 degrees. So I'll kick it up. I'll just kick it up to 20 degrees. So somebody's pulling at 20 degrees. And I'll go to right here. So I'll call this 1, 2, 3, 4, 5, 6, 7, 8, 9. So its distance is 9. So you have a vector operating. I'll operate it this way. And then what I'll do is I'll say, well, now I've got to also do a reasonable job of putting 20 degrees there. Here's your 0 degrees. You kick it up, and you're going to kick it up to 20. Now I'm going to do another one, which will be kicked. All right, I'll just make it 2 20s. Well, I'll make it 30. So there's your 30. I'll put the right there, and then, well, try to get it the best I can with my finger. And I'll go out to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is of length 10, and it is kicked up 30 degrees from here. Now, somebody wants to add these 2 vectors. I guess I could call this one A and this one B to get together so that I would have a new vector C. Now, how would I do this? Okay, the magic of this lecturing type is such that I can do a control C, and I can do a control V, take this, put it at the end right there. Now, I'll try to do this with this one. Hopefully I don't pick up any extra. Copy and paste, take that one, put it about right here. Now, I'm going to try my best to do a reasonable job of drawing this. Looks like the answer, and I'll go ahead and use a different color here, might be around 6 degrees up. But oops, look at that. I changed the color there without, here. I'm going to hit it here, then I'm going to change it to that. Oops. That's, you know, close to 6 degrees up. Now, if I count, I'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Gosh, it looks like it's about 17 visually. It looks like it's kicked up at about 6 degrees, but I don't know either one of those. I should not know that. Let's see if I can get that distance and the value there. So let me first move this 9 over to here, and I'll say the distance, the length of this is this. So what I'm going to do is I'm going to attempt to copy a portion of this, okay? And I might get some extra superfluous information. I'm going to copy, I'm going to paste this right here. I'm going to try to move the screen over, and I'll just, maybe I'll operate right down below it. So I'm right down here below this. I'm going to go ahead and take off this and this information. I don't know those yet. I'm not supposed to know those yet. So here, let me get this off. So here's what I'm looking at. Now this is the part that, and I've seen people who are very good at this. Sometimes I have trouble with it. I've seen it's no, of course, and you can tell I'm kind of off a little bit. But so, first thing, okay, let's take a look at this. I copied this one over to there. If I did, and I've got a vertical line where I kicked up 30 degrees. Now, I've got this one kicked down, so I know that this one is supposed to be 180 minus 20 minus 30. Those two go together to give you 50, get you about 130 back out of it. Now, I think I have Octave installed here. For those of you who have taken, and probably no one has taken this yet, so there is a software package called Octave. Let me take a momentary side tilt here. Eventually you will take a course which is MCEG 3003, which deals with something called MATLAB. Now, MATLAB, of course, has a lot of information. It's a very good program, but if you're at your house and you're learning the material, there is this, which syntactically, it's the same as MATLAB. In other words, if you took this code right here and tried to run it in MATLAB, it would run and give you the same answer as it would in Octave. So in other words, if you want to, you can download this to your computer and then install it. Now, the thing is, I've already done that. So I'm looking at the screen here for Octave, and I'm going to use it as my calculator. So here's the thing. I'll just take off and do it. 180 minus 50 gives me my 130. Now, I'm going to bounce back and forth between these two. Try to keep it at the top left because my drawing is down here at the right, bottom right. So, fact of the matter is, I know the length of this one is 10. So what do I know here? I know a length, I know an angle, and I know another length. Ooh, wait a minute. This puts me in the realm of knowing. Let's take a look. at the law of cosines versus the law of sines. What do I need to know? If I know a length and the angle between it. So if I know A and B, B and A, and I know the angle between them, I can find this. So with that in mind, let's go ahead and do that over here. So, law of cosines. Okay, I guess I need to call out what this side or length is going to be. Oops. So, that's going to end up being, and I'm just going to, instead of listing them as symbols, I'm going to list them 9 squared, 10 squared. 2 sides minus 2, 9, 10, cosine the angle between them, 130. So, let me take a quick pause here for something. All right, I'm back. Sorry about that. Had to pick up something. All right, so let's head off and go to, let's see, Alt Tab. Oop, not that one. Alt. That'll put me back there. I'm going to Alt Tab it to here. So here we go. Square root of 9 squared. I need a keyboard that's lit a little bit better than this. Minus 2 times 9 times 10 times cosine in degree. There's a D right there that you have to have. And I think that closes me out. And look at that. Pretty close to 17.225. Now, that's pretty close to that, so I feel comfortable now. Now the next thing is, what do you think this angle should be? Okay, so we measured and looked at this being kicked up at about 6 degrees above the horizon. So let's take a look here, and let's think about this line itself. Okay, I'm going to make this in blue. So if I drew a line that was straight out here, I'm going to argue this 20 degrees sits here, so that this should be a total of about 26 just from an eyeball that I did previously. Now, with that in mind, let's go find the answer. Okay. So, now that I got this on this side, I'm back in the realm dealing straight with laws of sines. Here's what I mean. It is true I could go in here and use law of cosine, and there's an advantage to that. But now I know these four. So now, if I want to know B, I can cross the angle B. I can cross across with this and pick up the C and the C. So I can pick these two up, and then I can pick the B up and leave this. So that's the case I have back here. So let's sort of take a look at here. So we're going to do our ratio here first. Since I'm going to want, okay, I better start listing these out. I'm going to call this a little a for being directly across from here. And I'm going to call this a little b because it's directly across from that 10, which I called that b. So that being the case, I go in and I'll say, well, sine of, we'll just go after b over b is equal to, and now I'll call these other things c because that's kind of what they might be. All right, sine of c over the big C Well, it turns out I can figure this out. This was given to me kind of offhand, whoops, as sine of 130. That didn't work out. 130 over 17.225 and some extra digits, which I can carry these inside of octave there. And then I got the b. Over here, this b is 10. So if I do the sine of b is equal to 10 times the sine of 130, 130 over, here, let's put it up here, 130 over 17.225, then I can just back this up and say sine inverse of this would be equal to the angle B. Let's see if in fact, let's go back to this. Oops, I'm going back to the wrong thing. Here we go. I'm going to call this, okay, wait, let's get this associated with that. Okay. What I'm going to do here is I'm going to go back and say I'm going to carry this as the length of capital C. Okay, so there's my length of capital C. So what I'll do is arc sine degree, to get me back in degrees, the value of 10 times the sine in degrees of 130 divided by that big C up above gives me back 26.406. So B is equal to 26.406. Pretty close to that 26 I guessed. So you can see just by using a ruler, I got a good approximation at the answer right here. So that's pretty reasonable. The answer I got was pretty reasonable. It gave me a guide as to whether or not I goofed this thing up here or not. So the last thing I've got is A. Now there's two ways you can get A. You can go back to law of sines, or you can say A plus 26.406 plus 130 equals to 180. And you could extract that out and say A is equal to 180 minus 130, which gives you that 50. I'm sorry, 50 minus 26.406. We're going to do this two ways anyway. So here, let's go back and see what we got there. Okay, so 180 minus 130 minus, you know what? I'm going to go up one angle, and I'm going to list that as a little b is equal to. That way I can put it in there. So the angle A would equal to 180 minus 130 minus B, which would give me 23.594. 23.594 for A. Let's check that with law of sines here. Okay. This is also going to be equal to sine of A over the A. In this case, okay, so here we're off doing this part. So in this case, the sine of A is going to be what you're looking for. The big A is going to be the 9. Okay, this is an A here. That is a 9. So this means A would be equal to the sine inverse of 9 times sine of 130 over 17.225, or in fact A would be equal to, let's head back over. Okay, now what I can do is I can jump back up until I find that, and what I can do is put in 9 there instead of 8, and I'll say A, the second rendition of A, 23.594. 23.594. So Pretty good. So there's an example of how you go through and do those. One I just made up pretty quick. Used the ruler, worked out very well. So let's go back to the book here. So in fact, that's all you do. If you go through here, you'll find all of these are the same thing. When you have a force here and a force here, what you do is you decide which part of the triangle you're going to use. You're either going to use this triangle or you're going to use this triangle. By the way, they're the same. They're just mirrored along. If you look at it, they're mirrored. This is mirrored along that side, kind of. Mirrored in two ways, kind of flipped. So it doesn't matter which one you use. He's used the bottom one. He used his information here, and then he's figured out, okay, so there's two ways to do this. Okay, so he has this being 115. So as he flips it over, he gets the 115 there. He ends up with the same circumstance. He knows this distance. He knows that distance. He knows the angle between them. He can immediately go after the resultant force. Then from that, you can take the law of sines and pick up these two angles, which he may or may not be asking. Well, he inadvertently did ask for it because he wanted to know the angle with relation to this. So he wanted to know this. Well, in order to do that, you need this angle, and then you add 15 to it. So there are questions in the book that are related to stuff like that. Here's another typical case, okay? So here you're resolving this 600-pound force to be carried between this link and that link. Now, the links themselves can only take an axial load, so essentially this load sits inside this link, and this load sits inside this link. So if you want to look at it from that perspective, he has listed them, drawn the 600-pound out, and said, okay, I got 600 pounds, and it's going to be offset by this and this together, so these all have to add up. Again, you're kind of stuck in, you're kind of stuck in the concept of once you draw this out as a vector diagram, you don't really need to do this triangle and that triangle. You need to pick one of them. He has chosen the upper one. What you find out is, think about it about mirroring about two axes. This triangle is equivalent to that triangle, just mirrored twice. So he took his angles across. Now he's got something totally different. He's got a 30 degree, a 120, and a 30, and he's got one load. So now you never have to use law of cosines, because the law of cosines, remember, relates to, I know this, I know that, I know the angle between them. Law of sines relates to this. I know, first of all, this, the angle directly related across. That gives you the ratio. Then you got to either know, like in this case, the angles or the lengths. If you know the lengths, you can get the angles. In this case, you know the angles, so directly opposed, well, this one will give you the, okay, let me zoom in on this. Law of sines relates this angle to this one. It relates this one to directly across this one. And I don't think I have, yeah, I got a green. It relates, this to that. So I'll get back to the blue. So that's what law of sines does. Now the key is you got to take a physical drawing and break it down to a vector. And so you see he never used law of cosines. So he has another example. This one's not really color-coded, but it's okay. So you've got 200 pounds. Okay, determine the magnitude of the force F and the magnitude of the resultant force Fr is directly along the positive axis. So in other words, this is kind of the invert. I know that it's got to be pulling it straight out of the ground. So it has to be like this. So I'm going to do it, and I'm going to assume this is 200. And then what I'm going to do is I'm going to assume that these, so in other words, the scale of that is exactly 200. So now I'm going to just draw a line and do the best I can about drawing that line. And then I'm going to copy that line. I got it. I copied that line to the base right there. Now, what happens is it goes to right here. It can't go further, because if it goes further, the resultant force kicks off to the left. If it's shorter, it goes to right there. So it has to be exactly this length. If in fact this is to scale and that's 30 and 45, I would guess that, that distance, maybe this is about 200, so maybe this is around 300, a little under 300. Looking down here, looks like F is going to be 250. So this distance ends up being 250, when this distance from here to here, so this ends up being 250, or was it 245? I'm sorry, 245. 245, and the other one ends up being slightly higher at 273. So again, reading the words really close, it says the magnitude of the direction of force, if R is directed along the positive y-axis, meaning it has to go vertical. This would make better sense if the drawing was such that instead of this, there was a chain and like a barrel directly under it, and said, okay, this has to go due to the physical laws of nature. This going down means that has to go straight up. But his drawing looks pretty good. Looks better than what I did. Here you have another case like this, and this is the whole point. Okay, the required resultant force acts along the eye bolt. Be determined along the positive, that F2 have a minimum magnitude. This is the F2, by the way. So here's what we're going to do again. Let's assume that this is to scale, and this is 800. And then I'll just draw a line that just continues down to here. I'll take that line, I'll copy it, and tried to do the best. Oh no. Okay, so let's do a Control Z. For some reason, I got both of those. That didn't look right. Okay, so here. I don't know what to do now. Here. Escape. There we go. So I'm going to try it again. I'm going to try only to copy. It's copying both. Here. Let's try this. I'm going to select that line. Then I will go to here. And then I will do a select. Now I'll copy it and put the end right there. Now, okay, so now I'll go back to my colors and hit the escape. And now this vector goes straight to the right, ends up right there because that's what it has to do. But it turns out that it says, now think about this, it is required that the resultant force acting on the eye bolt in figure is directed along the positive x-axis. Okay, so it's determined that. But determine the magnitude and the theta of the corresponding resultant force such that F2 is a minimum. So that means the distance from here to here is a minimum. So I can take this angle and kick it down, and I can kick it down, I can kick it down. It has allowed me to change this theta as well as F2. But it has to be that it goes along this line. So my first thought is, okay, just like he's done, he's produced several of these. This length is larger than this length, which this length is also larger than that length. Turns out that if this is 90 degrees to here, that's the minimum. And so you have a triangle, which if I can do, I can erase mine and work on mine a little bit better. The actual answer here is a perfectly vertical line dropping right here, and this vector resultant being right here. It is true, the resultant does go directly to the right. It is true that this F2, which can vary in its direction and length, such that this is the minimum F2 required to pull this thing, or you pull this thing straight down such that the resultant is going directly to the right. So this is an interesting special problem. Now, here's the other approach. If you use the I and the J, where you represent F1 equaling to some value plus some value J, and then you want a minimum, a lot of people will say, okay, I'm going to come up with the resultant vector FR, which will be a function of theta and, I guess you could say, the length of F2, and I want to take the derivative with respect to either one of those and set it equal to 0. That's a lot of math that you have to go through that you didn't have to do if you just looked at it on the page and looked at it visually. So this is a perfect case for why you're going through vectors laid out on the page this way instead of immediately going to f is equal to fxi plus fyj, and g vector is equal to gxi plus gyj, and adding them together, because he's asking you something different here. He's asking you to find a minimum of something or to make sure the magnitude is going in a particular direction. You can do it this way, and if you want to, I say have at it, but you'll spend a lot more time than someone who visually looks at it and figures out what's happening here. Okay, so here's some, okay, those are weird ones. I don't know what, this is something new that's in this edition, and I just kind of ignore those because it looks like they were just haphazardly put there. These look more, you know, the fundamental problems exist in this edition and all the previous ones. So what we'll start doing tomorrow is just plucking out one after another of these and working through some of them, and then we'll be able to go straight into here. And in the coplanar, one of the things you see is that, and one of the things is when you're adding these, guess what? Nothing new. You just simply add all the components with respect to I. Oh shoot, here. Then all the components with respect to J. And if you had K components, you would have all those summed up with the K here. In this case, you're just summing the components. So you take this part, that part. So you take this distance, you take that distance, and then you take this distance. You add those all together for your X component. You take these, add them together, get your Y component. So you're breaking things into components here. And then we'll get to the all famous equation right there. And so for that matter, we got enough time to finish this out. Let's go ahead and do this lecture, and we'll work problems in the previous and in this one next time. So here, what is this? Coplanar, we got 5 minutes. We can do this. You got fx and you got fy. You got two ways to determine that. Well, you could be given the angle, or you could be given the slope like this. Okay, take a look real close. This one's pretty normal. Fx is equal to f times cosine theta. And then fy is equal to this distance, which is, sine of theta. So you take this distance times the sine of this theta, it gives you that distance. So you get their x and y components that way. Here, it's more of a ratio. So if you knew this, and you knew these three, you'll know a over c is ratioed as fx over a. A over c, f, the total. These are not vector components now. They're the lengths of the vectors. Typical example that you'll see in the book, 4, 3, 5. If this is 50, then this is 40, and this is 30. So the ratio is the same. In other words, if I look at this ratio to this being parallel to that, this being parallel to this, I look at 4/5 of 50 to get 40. Now let's go to the other one. If I want 30, I take this ratio to that. So 3/5 of 50 gives you 30. And this is what he's talking about throughout this. So take a look at that. It's fairly simple, straightforward. Geometrically, it makes sense. Now, I have seen people do this, and it's just extra computation that you might just enjoy doing, but it takes time. So this angle, same as that angle. So, okay, if you look at it, you could say, okay, what is that angle? That is cosine inverse of a over c. Then you say fx is equal to, okay, so what is this? Fx is going to be equal to the cosine of whatever that angle is, of inverse cosine of a to c times this distance, or say 50. Okay, so guess what? You take cosine of the inverse cosine of some value v, and you're going to get out the value v. So you end up with fx equaling to a over c times f. And that is what sits right there. So you can take the extra point to, this angle is equal to that one, and that angle is equal to this off of this triangle. You will get the same answer. The problem is you may take the intermediate step and write down the angle wrong here, and then get the wrong answer because you took too many computational steps to the answer, and you took too much time to get there. So be thinking about that way. The least number of computations from the given information to the solution is the best way to go, because there's the least chance of messing up with your fingers on the keyboard. Okay, we get down to here, and you already know how to add these. We talked about that 5 or 6 seconds ago, and that's all you do. Then, once you get all those, you can find the resultant value by squaring it, and then taking the square root, and then you can find your angle. Now you can do a tangent, but you can also do a sine or a cosine, an arc sine or arc cosine, whichever one you want to do. You got to be careful here, because sines, arc cosines, and arc sines, and arc tangents are very limited in a calculator space. And I don't have enough time, but I'll talk about that maybe next time, or as we go through these problems. So here's a typical case. You break down into components, x component, y component. You find the resultant, then you find the angle. Now, you go down here the other way, and okay, Cartesian vector notation. Well, okay, so really, essentially, they're the same thing. So I'm sorry, they're the same thing. It's not really, this is kind of silly, but yeah, so you put them into the two forms. You basically have these two. It's the same thing that you get out of both of them. I'm not sure why he has those two different ways. But we'll come back and work one bunch of these, and we'll work a bunch of those other ones on Friday. And so I think at this point, my clock up here to the right says 11:50, so it's time to go.